let us discuss multiplication of two large integers using the first divide and conquer recursive algorithm. Let's assume there are two numbers a, which is represented as a1 a0 and b as b1 b0, where b1 and a1 they represent the first n by 2 digits of the number, and the second part, that is a0 and b0, represents the second n by 2 digits of a number a and b, where both a and b are n digit numbers. So if we were to multiply these two numbers by making use of this first recursive technique based on divide and conquer strategy, then this is how the multiplication would happen. C is equal to a into b. That would mean further multiplication would be C is equal to a1 into 10 raised to n by 2 plus a0 into b1 10 raised to n by 2 plus b0. This can be further expanded to get the equation given below. For instance, consider these two numbers 1, 2, 3, 4, 5, 6 and the second number 1, 1, 7, 9, 3, 3. If we were to now multiply these two numbers making use of the divide and conquer recursive strategy just mentioned above, then this is how the actual multiplication would take place. If we have a closer look at this, it would be easy to understand. So a into b would mean multiplying 1, 2, 3 into 10 raised to 3 plus 4, 5, 6 and so on. Same thing can be written more formally in this way. So we are saying there are two numbers a and b of type a1 a0 and or rather represented as a1 a0 and b1 b0, where a1 a0 b1 b0 are n by 2 digit numbers and a and b are n digit numbers. And now we want to multiply them. So we would multiply them in a typical way, which is a1 into b1 into 10 raised to n, which means we are multiplying the first half digits and then multiplying it by 10 raised to n, followed by the middle numbers, wherein we say a1 into b0 plus a0 into b1 into 10 raised to n by 2, and then the last part, a0 into b0. So what is more, without really getting into details of the algebra, of course, though the algebra here is pretty simple to understand, the highlighting feature here is how many multiplications do we really need to make the computation. What we are really trying to target is, by making use of divide and conquer strategy, we want to minimize the amount of time required to do the multiplication, as against maybe brute force method. So if we divide by the way mentioned in here, how many multiplications do we need? How many multiplications? So we actually need, if we count, we need 1. This is the first multiplication, multiplying a1 into b1. So 1 multiplication. This is the second one. This is the third one. And then this is the fourth one. So we actually need 4 multiplications of n by 2 digits. Hence, representing this as a recurrence relation would mean the recurrence relation is t of n is 4t of n by 2. This 4 coming from the fact that we have 4 multiplications, and 4t of n by 2 coming from the fact that we are dividing the number, or rather the problem size, into half its original size, plus theta of n. If we expand this further and solve this further, what would be the amount of time, or what would be the amount of time required? If you remember Master's theorem, then one should be in a position to quickly say that the complexity here would be O of n square. So now so what that means is the complexity is still O of n square, which is similar to what the complexity was when we used brute force method, where again the complexity was O of n square. So let's try to look at a different technique, which is the second algorithm for multiplication of two large numbers. So the basics remain the same, but if you have a closer look at the algebra, it has been done a little more tactfully. So now we are saying C is equal to A into B, where C is equal to A1 into B1 into 10 raised to n plus A1 into B0 plus A0 into B1 into 10 raised to n by 2 plus A0 B0. So that remains the same. But what we are trying to say now is we are representing this with two constants, where we say C2 is 10 raised to n, rather it is equal to C2 into 10 raised to n plus C1 into 10 raised to n by 2 plus C0. The most important part actually comes here. This part I would suggest is most important, where we are saying C2 is A1 into B1, which is the product of the first half. C0 is A0 into B0, which is the product of the second half. That is self-explanatory. C1 is the most important part. What we are trying to do here is, though C1 would actually means is A1 into B0 plus A0 into B1, by making use of algebra, we have been able to reduce the amount of calculation required and reuse the results of the first two components that we have already solved. So C1 could be represented as A1 plus A0 into B1 plus B0 minus C2 plus C0. So C2 and C0 are the two multiplications that we already have with us, and we have now introduced a new multiplication, which is the third multiplication for the calculation of this C1 component. So now what we have with us is the multiplication of two numbers A and B represented as C2 10 raised to n plus C1 10 raised to n by 2 plus C0. So a closer look at the same thing helps us to identify how many number of multiplications are needed when we do computation this way. So can anyone answer how many multiplications are needed? So it's very simple to just count the multiplications. It is one multiplication here, the second one out here, and the third one out here. So by making use of this technique, we needed only 3 multiplications as against 4 in the earlier technique. Hence, the recurrence relation of this technique can be written as T of n is equal to 3 T of n by 2 plus theta of n as against 4 that we had earlier. And if we apply Master's theorem once again, what we get is the complexity, or rather time complexity here is T of n is n raised to 1.58 as against n square, which we would achieve in the earlier case. So by tactfully using algebra and reducing the number of multiplications, we were able to multiply two large integers in time which was less than what we would otherwise require. Thank you.